You can get equipment damage without having direct lightning strikes to your building or facility. I could name many not well-off countries in Asia and elsewhere that put a lot more lightning protection in than Australia does for the same level of lightning activity. So that's one of the myths about lightning and lightning protection, that the object has to be conductive.
Just sat down with Franco from LPI and we talked about, of all things, lightning protection. Now, this is a really fascinating subject, and we sort of concentrated on the application when it came to commercial solar farms, any ground mount systems. We covered a lot of ground, went into a fair bit of detail, but Franco has promised to come back for part 2 where we go really into the deep and nitty gritty. Now, before you sit down and watch this podcast, don't forget to like, comment and subscribe to the channel, and of course to Greenwood Academy. Sit yourself down, strap yourself in. Let's talk lightning protection. Where did you grow up, Franco? And I assume you're Italian background. Is that right?
Yeah, look, my parents were migrants from Italy after World War II, and I was born in the 1960s. I'm giving away my age.
Like me, 63 my end.
That's it. Well, you got a year or two on me then.
Right.
I guess, growing up in a migrant family was interesting because Australia was quite British, I guess, in that era, but I only spoke Italian at home.
Yep.
My parents, their English was so poor that my mum said, well, you're only going to learn Italian, you'll learn English when you go to school.
Yep.
So I went to school at 5 years of age, not speaking any English at all.
Wow, yes.
So, yeah.
But you would have picked up quick. I mean, children pick it up fairly quickly, don't they?
I picked it up, but I had to go into remedial classes until about year 6 in primary school.
Yeah,
so
right.
I'd have to go off to which was good of the school to do that, actually, to cater. Individualised learning wasn't a thing back in the 1960s.
Yeah, exactly, yeah.
So I'd accelerated my English to the point where in year 7 I was back in the top class in English and actually teaching the Australian kids a bit of English as well. So.
And the advantage of being bilingual as well.
Yeah, and a lot of the research shows that that's actually a good thing to be bilingual or trilingual.
Absolute bilingual, multilingual. It's good for that left side, right side of the brain hemisphere. Same as playing the piano and a lot of other things.
Exactly.
I grew up similar to you. My mother was Anglo, but my dad was Serbian. But we didn't learn Serbian because there was a real Anglicisation, if that's a correct word, and much to my chagrin, didn't learn it. I can swear and count to 10. Did you grow up in Victoria or?
No, I'm Tasmanian.
Oh, you're Tasman,
I can show you the scar on my neck.
Yeah, a mate's got a T-shirt. He lives in Tassie that's got the two-headed.
No, I was born in Launceston and I grew up there. I'm based in Hobart now since 1997, so 29 years ago.
Yeah, wow.
I moved to Hobart. But, born in Launceston, same as Ricky Ponting and, all the David Boone and all those famous cricketers.
Are you a cricket fan? You mentioned.
Oh, I love cricket,
yeah.
I mean, I used to play social cricket myself a bit, but I never played it seriously, but I love cricket, in the summer.
So you've gone to primary school in Launceston in Tassie and then moved on high school still in Lonnie?
That's it, It was St Patrick's College, actually. So, so that continued from primary to secondary school.
And were you one of those kids who sort of knew exactly what they were going to do fairly early on, or?
Look, in grade 4, I was absolutely 100% certain I wanted to be a teacher.
Wow.
Yeah, a maths science teacher.
Right.
Because I loved mathematics and science. Didn't really like art very much. I did okay in all those other subjects, but I just loved maths and science. So I wanted to be a teacher.
And when did you sort of realise, like, because obviously you got an engineering degree, I assume, and I without checking my notes, I can't remember what it is actually. But was there a point in high school where you went, I think engineering might be the go?
Well, actually, I have a science I did a science and education degree at university.
Right.
So I did a double degree. Then I went on and did my doctorate, which was in experimental physics, believe it or not.
Wow.
But, and in astrophysics, in radio astronomy. But soon after I finished my doctorate, I actually changed fields completely, and it was called lightning protection.
So I got to be very careful when I say something like it ain't rocket science, because
that's right.
Yes.
Yeah.
One
thing that having a scientific background, although I've been doing engineering for the last 29 years, really, it's electrical engineering, all of that stuff. But one thing, having the scientific background, it gives me a completely different perspective on how to tackle a problem to what some of my colleagues who came through engineering only. So engineers are very practical and, build things and whip things up quickly. Scientists tend to ask the why and how first and do some preliminary work before trying to formulate a solution.
Right.
And, don't automatically assume that there is a solution. So engineers are very good from that point of view in being very confident that there's always going to be a solution for something.
But invariably, isn't there always a solution, whether we find one or not?
Look,
I'm being a bit philosophical.
I think so, yes. Yeah. But it's how you go about finding the solution that's actually a little bit different when you have a scientific mindset to an engineering mindset. But having said that, I've been in an engineering environment for the last 30 years almost.
Gotcha.
So a lot of that's rubbed off onto me. But I'll give you an example. So the way I would tackle a new problem is to do a literature search first.
Okay.
So I try and find out as much as I can that's actually out there in the literature before trying to come up with something new. And I have done quite a few new things in my lightning protection days, patents and so on. Whereas an engineer probably will ignore all of that to some extent and just go straight for the solution that's in their head based on their experience.
Which may have already been found out. So they've wasted their time.
Potentially. I'm not saying that that's what I've seen lots of examples of.
Okay.
But, that's how in the science world you're trained to do the literature search first always. Right. And even when writing a paper, for example, you've got to do a literature review and have that as the introduction.
Wow.
It's a little bit different, but of course the objective is the same in both fields. So
this study, science and education double degree, happened at what University of? Where did it happen?
What was University of Tas is University of Tas now. It was an institute of technology back then, and I finished that in 1986.
Yep.
A long time ago.
Yeah.
And then, wanted to go out teaching, but I very quickly learnt that teaching was about babysitting and policing rather than the love of the subject and students wanting to learn that subject matter, whether it's mathematics or science. So I became disillusioned pretty early on with that.
Yeah, right.
And so I continued on with my studies, postgraduate studies.
Hence the doctorate. And
I got a job at UTAS as a lecturer, but the condition was I was on contract.
Yep.
And everyone's expected to do a doctorate if you're going to be a university academic.
Yes.
So I started the PhD program, and I was teaching microprocessor electronics and physics at university.
Interesting.
So electronics is a very practical engineering type undertaking. And so my master's program that sort of turned into the PhD later was in microprocessor electronics as well, but for a radio telescope in Tasmania for the 26-metre dish.
Yeah, so explain to the people who don't fully understand that what a radio telescope is. It doesn't use optical lenses. Is that correct?
That's right.
Yeah, okay.
It's a bit like a satellite dish. Right. So it collects radio waves coming from the universe and focuses them on the focal point of the dish, a bit like those small dishes people have on their roof.
It's like a parabolic.
That's it.
Yeah.
And the receiver, which is at the focal point, is a very, very sensitive piece of RF engineering. It has to be cooled with liquid helium to very low temperatures to minimise noise and all of that. I'm having to dust off my work from 30 plus years, 40 years ago. And then that gets turned into an electrical signal, and then that data gets recorded, and then you analyse the data. So radio astronomy is very much about it combines electronics and electrical RF as well as signal processing. So most of my doctorate was actually signal processing. So that's writing code to analyse data.
What code would have that been back?
It was
COBOL,
Fortran.
Fortran,
yeah.
right? Yes.
So I wrote tens of thousands, if not hundreds of thousands of lines of code to analyse. I studied pulsars, which are neutron stars. So for those listeners that don't know the basics there in astronomy, very simply, stars, when they die, either become a white dwarf or a neutron star, which is called a pulsar, or basically a black hole.
So why do they call them a neutron star? Because there's all the neutrons. Yeah,
it's made of neutrons.
Right,
so it's basically something that's like 10 or 20 kilometres across, spinning very fast, and it's basically mostly neutrons, very, very strong magnetic fields. So those magnetic fields actually cause a pulse, a pulse of radio waves every time it spins, and we pick those up and we accumulate that data and can actually characterise these neutron stars.
Are they dense bodies?
Very dense.
Yeah, but not as dense as a black hole.
Well, I don't know if you can exactly compare it like that, but the analogy is a teaspoon of neutron star weighs, I don't know how many tons it is, but it's in the tons, 1 teaspoon of it.
Wow.
So that's how dense they are.
Okay, so we're talking about matter being compacted, so the voids are virtually non-existent.
That's right. So it's compacted right down, but it hasn't done what a black hole does, and that is it goes into a singularity because there's so much mass.
Wow, this conversation is a podcast in itself, isn't it?
That's right.
I think we'll move on because personally, I'm fascinated by all of this. It's but I've still got my Greenwood hat on, and I have. So
of course.
So you're at the University of Tas, and you're lecturing, etc., and then you're going, okay, I'm not a big fan of the lecturing. I want to do a little bit more. When did you start to move into the whole lightning protection? Mm-hmm. Yeah, and because that's what you're doing now. That's what you've been doing for a very long time. Yeah.
A very clear cut move. So I'd been at the university for about 8 years, and finished my doctorate. And look, there was a lot of politics and all the usual thing that goes on in universities. But in the end, I thought I don't want to be an academic for the rest of my life either. I mean, I was very good at it. Got very good reviews of the teaching and was publishing papers out of my research. But I thought I want to actually go and work in the private sector. So that meant having to change fields.
Yep.
So I started applying for jobs, and interestingly, I got a job offer here in Melbourne from a company that models ships going into harbours and whether they're going to scrape on the bottom.
Okay.
It was a very interesting job. It was a bit of hardware.
It's bathymetry.
I can't remember the name now.
I find it hard to pronounce. The only reason I know that word is because we did a floating solar array, as you probably know, and we had to bathymetry. Yes.
Right.
Yeah. Surveys. So okay.
So I got offered a job, but my wife at the time wasn't too keen to move to Victoria.
Yep.
So that didn't happen, and then a job came up in Hobart with a company called Global Lightning Technologies, and it was a standout company in lightning protection. 120 employees at the time.
Wow. For
a Tasmanian company.
That's a pretty damn big company.
Yeah, exactly.
It's such a specialised area.
In a niche area, yeah. So anyway, I got offered the job there, and I moved to Hobart. I had a 2.5-year-old and a 6-month-old at the time, or it was like 2 and 0 almost.
Wow.
And but made the move, and I've been in that field ever since. So I worked as a sort of almost a research scientist in those early days, in the engineering department, but did a lot of practical stuff, and then moved more into other areas like consulting work, product development. So I sort of covered the full spectrum of sales as well now.
Is it true that most of your work is for overseas customers, or is it like without going to the nitty gritty of commercial confidentiality and all that? Is it a fair whack outside of Australia?
About 80%.
Wow.
Yeah, it's quite a lot.
Wow.
I mean, Australia, if you look at Australia, it's just one country and it makes up 2% of the world's GDP, I think, or it might even be less than that. So we're a global company.
Yep.
Now, there are a lot of steps between that job that I got and where LPI is today. So if you want, we can fill that history in briefly.
Yeah, please.
But basically, we service up to about 80 countries around the world in the present day.
Wow.
So, yeah.
And is it, from the perspective of the Australian market, is it because we are small population-wise, or is it also a combination of the fact that, the actual light, how do I phrase that? Things are more lightning prone in other areas than Australia. Is that a correct assessment or not?
Oh, look, it's a very fair question.
Yeah.
Australia has quite a bit of lightning in the northern half of the country.
Well, Darwin's the capital of the world, the lightning capital.
Well, not the highest in the world, but it's...
I thought, okay.
No, well, relatively speaking, so Darwin gets about 80 thunder days per year.
Right.
Of light, so that's 80 days per year where there's lightning. Singapore gets about 200, 150 to 200. Okay. So the more on the equator you are, the higher it is. But it's still Darwin and Northern Australia is pretty high, right? The southern parts don't get much lightning, like Victoria and Tasmania, for example. But when we get a storm, like Hobart had a storm about 3 years ago, one storm for the year, 4,000 ground strikes. And it caused a lot of damage. So just because there's not a lot of lightning doesn't mean there's actually not a need to mitigate against lightning.
But the number of lightning strikes sounds like it's correlated towards the closer you are to the equator.
Exactly.
Okay, and why? We're getting a bit nitty gritty, but why? Why is that?
It's not nitty gritty. It's very simple. Basically, a thunderstorm requires humid air rising very fast.
Okay.
That's what creates those big black clouds called thunderclouds.
Yep.
So near the equator, obviously that's going to happen a lot more easily than in Antarctica where there's no lightning, for example.
No, but why does it happen more easily at the equator?
Well, it's because it's hot.
It's a temperature
and
thing.
the air's humid.
Okay, so more hotter temperatures, more humid. So you have to have both humidity and temperature.
That's right.
Okay.
But having said that, there are winter thunderstorms where it's not hot and humid. So this is where it gets a bit complicated.
Okay.
And probably that's too nitty-gritty for today.
No, we'll see where we go.
But the basic picture is the equatorial regions have the most lightning activity. So that's why the north of Australia, being closer, has a lot of lightning. The south of Australia doesn't. So to answer your original question, though, Australia very much has a she'll be apples attitude. So let's not get into politics, but let's look at our fuel reserves that have been shown up of late. That's just a classic example.
That really dates this podcast, but you're right. You're dead right. You're dead right.
Yeah. So with lightning protection, even though there's a lot of lightning, there's not a lot of attention paid to it in Australia. I could name many poor countries, not well-off countries in Asia and elsewhere that put a lot more lightning protection in than Australia does for the same level of lightning activity. So it's just not taken seriously here like it is in some other countries.
Wow. I think you're right. It might be that she'll be right attitude.
That's what I think it is, yeah.
Okay, well, let's go to what actually lightning is and how it forms. And I'll start off with a question. Does lightning only come from clouds, or does it come from the ground and the clouds?
Okay, so needs a bit of a background there.
Yeah.
But basically, that fast rising air I was talking about, what happens is the theory, and the science is still not well understood. Lightning research is really only seriously been done for 100 years. So compared to other fields, it's still pretty young.
It's new, yeah, gotcha.
But the theory is that those air molecules rub together, they get charged up, and that charge then gets separated in the cloud. Typically, you get negative charge at the bottom of the cloud and positive up the top, but not always.
So we talk about negative ions and positive ions.
That's
here.
it,
Okay.
yeah, charges,
Yep.
yeah. And then so that charge builds up to a point where it breaks down the air in the cloud and it starts to come down towards the ground, which is the opposite polarity.
How, when you say it breaks down the air, what, are we talking like a plasma effect or what?
More, yeah. So the air, so electrons are stripped off the
Right.
molecules, and so it becomes conductive. The air becomes conductive.
Right.
So it starts with a thing called a streamer, and then it becomes a leader, but it's effectively a plasma.
Right.
It's hot, gaseous, charged air molecules that are almost like a liquid metal, so to speak.
And it's wanting to find a destination by the sound.
Well,
of
it's
it.
going for the opposite polarity, which the ground is oppositely charged to the
Right.
thundercloud.
Right.
So thundercloud's negative, the ground's positively charged.
And does that, when you say the ground, does that apply to bodies of water as well?
Everything.
Okay.
Everything.
Yeah, anything that's on the surface of the earth.
So then
Yeah.
what happens is on the ground you've got objects. So think of one of the skyscrapers in the Melbourne CBD.
Yes.
They are very tall,
Yes.
right? So what happens is when lightning starts to approach, a little mini lightning starts to come off objects on the top of buildings and off the tops of trees and other points around, depending on their relative heights and their shapes.
And that's because they're grounded to the earth?
That's right.
Aha.
So that's called an upward leader. So when that forms, it's called an upward leader. And so that upward leader keeps going towards the downward leader until eventually they meet. So the upward leader that's the closest or the fastest or the most advanced is the one that typically intercepts the downward coming lightning out of the cloud.
And at what point do they meet?
Well, they meet at a point where the upward leader has reached its length to intercept the downward leader, the downward lightning. So it's typically closer to the ground than it is closer to the ground. But it gets a bit more complicated than that. For a very tall building, you can get a thing called upward lightning. So what happens is the cloud is charged, nothing comes out of the cloud, but the building, a very tall, think of like the Burj Khalifa in the Middle East.
Oh, that's,
It's 860 metres high or something like
wow.
that. So off the top of that will be this upward leader, and the upward leader will go all the way to the cloud and cause a breakdown, the big bang and the flash.
Yeah.
So that's called upward lightning. So that only happens to structures that are over 60 metres high, but typically more than 100 metres high.
Right.
So the probability of that increases the taller the building is.
And is that a logarithmic increase or a linear one?
I think it's logarithmic. I'm trying to think, about what the equation is. I haven't looked at it for a while. But by far the most common type of lightning is the downward-upward scenario that I described first.
Now, there's a lot of different lightnings from a common name perspective. There's fork lightning. Actually, that's the only one. But I don't know there's one other weird one called ball lightning.
Yep.
And that behaves completely differently. Are you happy to talk a little bit about
Look,
that?
I don't know a lot about it. One of my research colleagues he's probably in his 90s now, John Loki, has written some papers on this topic. It's absolutely nothing like a conventional lightning attachment process.
Right.
Ball lightning is a ball of plasma that can go horizontally. So it's something completely different, but there's been a lot of research done by international researchers like in Russia is one particular place. And as I said, Dr. Loki from his ex-CSIRO has actually done quite a bit of work in this area as well. But it's, as I say, nothing like the standard lightning attachment process.
Okay, this is... All right, well, I think anyone listening has probably got a fair idea now what lightning actually is. And again, it's probably a subject for a complete podcast again. But let's look at what lightning protection is. And first off, why do we have lightning protection? What is its main goal?
Yeah. So, look, put simply, lightning kills people. It damages assets and blows up equipment, right? And the fourth one that often isn't discussed very often, but it's a central part of the IEC standard on lightning protection, is it starts fires. So insurance companies want lightning protection on buildings to avoid those buildings catching on fire.
As opposed to destroying the existing electrical infrastructure.
Well,
and that's part of it.
Both of them can happen.
But the fire's more.
That's right.
Okay.
So the electrical infrastructure can catch fire, and then that starts a fire, and the whole building burns down, so to speak. Or you can get sparking, and there's some material there that can ignite, and that starts a fire. So lightning protections, the aim of it is to mitigate those four main types of consequences that I just listed. To try and stop that happening. Now, you can't do that 100%. There's no such thing as 100% perfect lightning protection, so it's all risk-based.
Okay.
It's very much risk-based engineering. And typically, you look at reducing the risk from 99% to 84% is the usual protection range that you look at. So 99 is obviously the best and the most expensive.
Yes.
84 is sort of the bottom level, the cheapest sort of solution, but still doing something.
So from a
useful.
business perspective, like for instance with a solar farm, wind turbines, etc., you're looking at doing a cost-benefit analysis, going, well, this system will cost me X amount, but it'll mitigate these effects, which could cost us this, that, and the other.
Exactly.
Yeah. Gotcha.
So that's called a risk assessment.
Yep.
So there's a formal lightning risk assessment procedure that you can carry out. But the cost side, really, that comes down to the individual project owner or, the owner of the facility as to what their risk level is as well. So
from Greenwood's perspective, as you know, we do small solar farms up to 5 megawatt. We're now doing some BESS projects as well, up to 30 megawatt hour, and we've done some weird stuff like floating solar and also some agrivoltaics as well. So we're talking about aluminium structures that, well, not in the case of floating solar, but most of them are seated into the ground, whether they're rammed in, whether they're concreted in, et cetera, et cetera. So these are structures that potentially can I use the word attract lightning? Is that a fair assessment? Or?
Yeah, so I don't like the word attract.
Yeah,
I know
that's why I was reticent to.
So you think about the lightning attachment process. Lightning comes out of the cloud, and then you initiate an upward leader. And if you happen to capture the downward leader, then you determine the point of strike. So that's the process in simple terms. So you're not attracting from the point of view that there's anything special about it. Every object can initiate these upward leaders. Even a tree doesn't even have to be a conductive object.
Yes.
So that's one of the myths about lightning and lightning protection, that the object has to be conductive.
So with the tree, because we hear of trees getting hit a lot.
Exactly.
I've seen they call them lightning trees, and they tend to explode out at the base, and you've got this big, So what is it? Is it the actual liquid inside the phloem and the xylem that detracts, or is it the actual bark and? So what's the most conductive part of the tree?
So trees are not very conductive, right? So, but that's why, and wind turbine blades used to be made of fiberglass. Now they're carbon fibre, which is semi-conductive, but fiberglass is non-conductive.
Right.
They were getting smashed by lightning in the early days of wind farms. But to explain trees, so just remember always the process. If you initiate an upward leader, there's a chance that you're going to intercept the downward leader.
Right.
So even a human being, off the top of their head, if you're on top of a mountain, you have to initiate an upward leader to actually get hit by lightning. Okay, so the tree is the same, but it doesn't have to be conductive to start this breakdown of the air process at the tips of its branches. So what happens is the air breaks down there, a bit like it did in the cloud before lightning came out of the cloud.
Oh, okay.
And it gets longer and longer, driven by the voltage and the electric field of the downward leader. And then eventually, if it meets the downward leader, the tree gets struck. So why does the tree split? It splits open. It's because the moisture in the trunk gets superheated very fast.
Expands.
It expands and it explodes.
Gotcha.
And it can throw bits a long distance away.
I've heard.
Yeah.
I've heard. I used to be involved in conservation land management. We saw quite a few trees that have been hit by lightning. The other thing I was going to mention, I really like fishing, and one of the first rules is if you've got a carbon graphite fishing rod, don't be fishing when there's lightning around.
I would go further and say don't be out on the water.
No, of course. Yeah. I totally
because
agree.
Think about upward leaders. If the water's flat, the chance of an upward leader is pretty low. But if you're in a tinny, sitting up in a tinny, the chance of an upward leader from your head is very high compared to the surrounds. So what's going to be the most likely strike point?
My head. Gee, that's a really sobering thought. Look, it seems to me that with the lightning protection, and we'll get stuck into what the different approaches are, surely there could be a sacrificial tower. For instance, if you put say there's a building X and it has, it's been struck by lightning, it's one of the new high rises on the Gold Coast, because apparently the Gold Coast is getting pretty lightning-ish. That's not a real word. Can't there be another like a taller structure that becomes that sacrificial point where the lightning strikes? Is that a viable?
Look, what you've described is actually lightning protection.
Okay, right.
So the whole purpose of lightning protection is to put a prominent point up there that's going to be the most likely strike point.
Right.
So the technology behind that point, what I'm calling the point, but we call them air terminals, is where a lot of the science and engineering comes in, particularly with the last 30 years of research.
And are we talking about the shape? Oh, actually, I'll step back a little bit. Let's talk about what the components actually are for lightning protection. Now, surge protection devices are part of that implementation strategy. The lightning, I'll call them lightning rods, but they're not all rods. That's part of it. A system of actually carrying that energy into the ground is another, and in some cases there's chemical assistance, isn't there? People changing the makeup of the soil surrounding the actual lightning rod. Can you just expand on all of those? Yeah.
Look, and this is in all my presentations. The very first slide is what makes up a systematic protection plan.
Yep.
And it's 4 steps.
Right.
So step 1 is direct strike protection. So that's lightning rods or air terminals up in those prominent locations, capturing direct lightning strikes. So by that we mean capturing the lightning downward leader as described earlier. The second step is to put surge protection on all conductive lines going in and out of a facility, building or site.
Both AC and DC.
AC, DC, communications, signal lines, data lines and power lines. So that's to protect the equipment that those lines are connected to. Because what happens is, even if lightning doesn't strike that building or facility, let's say it strikes 3 kilometres away, the electromagnetic field from the lightning strike can induce surges on those metal lines, and those surges come in and blow up the equipment. So that's called indirect lightning strikes.
Right.
So you can get equipment damage without having direct lightning strikes to your building or facility.
And that's because you're connected via earth to another structure or another building? Like for instance, let's say a substation, solar farm, you've got a substation 5 kilometres away. Is that what we're talking about?
No, I'm talking more about lightning hitting the ground somewhere. So let's say lightning's hitting the ground, but the big channel, the big bright channel you see when lightning strikes, okay, that's actually a huge current, a huge fast changing current. So it has an electromagnetic field around it. That electromagnetic field will induce on conductors a surge, or what's called an impulse current or voltage.
Right.
And that then travels along that wire and hits the equipment and blows it up.
Is that the same way that an EMP would work?
Very similar, yeah.
Right, okay.
It's called LMP. So LEMP, lightning electromagnetic pulse.
Right.
Whereas, the
other one is
that's the general one.
Yeah.
Then you've got NEMP, which is nuclear electromagnetic pulse. So nuclear detonation, which is a much faster rising thing. But lightning's the second fastest rising spike, if you like, and that's what damages sensitive equipment.
So we're talking when the lightning hits the ground, its ability to travel, obviously, from an impedance perspective, is due to the conductivity of the ground itself. Mm-hmm. And different grounds have different levels of conductivity, don't they?
Yeah.
I know in the west coast of Victoria, in the basalt areas of Warrnambool, Port Fairy, they have a lot of issues even finding earth there because of the conductivity of the soil. So we're probably jumping ahead a little bit here. So as part of the lightning strategy, you've got the first and foremost thing is that lightning rod or air terminal, and then there's surge protection, and then after that?
After that, earthing and bonding, which you mentioned as well, and you were talking about earthing there a moment ago. So it's very important to get the impedance of your earthing system as low as possible because that minimises the rise in voltage that you get on conductors. So that minimises things like the probability of sparks and arcs occurring as well. So bad earthing can result in arcs and sparks within a building, right, which can start a fire even. So it's another integral part of the whole thing. And bonding, I want to mention bonding especially because if you have different earths...
We're talking about
equipotential bonding, So that's tying together different objects with a copper conductor or an aluminium conductor, for example, is one way of doing it. But if you have a lightning earth, electrical earth, telecommunications earth, and let's say, sensitive computer earth, it's important to bond all of those together with a metallic conductor.
But do you have to do that?
Well, if you don't, you're going to have things blowing up. So it's a really fundamental thing, and people have in their minds over and over again that if I leave them separate, then lightning's not going to get into these other ones.
But it doesn't work like that.
It doesn't work like that. So lightning travels through the ground, as you mentioned before, but more to the point, if lightning goes into its own earth, that earth voltage rises to potentially hundreds of thousands, maybe even 1 million volts, right? The other ones, because they're not bonded to that earth, stay at a lower voltage. The soil stays at a lower voltage.
Gotcha.
So that just drives a huge surge through the whole facility, and it just blows up all the things.
Following the path of least resistance, as always.
That's right. So bonding is a really important one. And then the fourth step in a proper protection plan is if you've got people outdoors, you have to protect people. So that's done through things like a lightning warning system or special mats that service personnel working on equipment can stand on a special mat.
Well, like an earthing mat, or what are they?
This The mat I'm talking about that we've developed is a cross between insulation and equipotentialisation. It's a big word. I'm glad I got it out.
You did well.
Got it out of my mouth, but it's got a conductive rubber layer underneath, and it's got an insulating layer on top, and
Franco, conductive rubber layer. But
that's
isn't
right.
Rubber fairly non-conductive?
If it's doped with carbon, carbon black, it can be made semiconductive. In fact, there's a lot of semiconductive rubbers in all sorts of applications.
Gotcha.
You would never imagine. And then in the middle between those layers is a stainless steel mesh layer.
Right.
So traditionally what utilities do is they give workers a copper mesh, a heavy copper mesh that goes on the ground, and they stand on that when they've got to throw a switch. So that's equipotentialisation.
Yes.
Or, as you've probably seen in some high voltage areas, people will stand on a thick rubber mat for insulation. Our EPR safety mat, it's called, is a hybrid between those two, and it's a lightweight portable mat that you can roll up and carry away.
And you've gone with stainless steel, I assume 316 marine grade.
That's right.
For longevity, etc. And you've gone for that. It's not as conductive as the copper, of course, but it'll last longer. It's more robust, and obviously you make up for that lack of conductivity compared to copper by having more of it.
It doesn't need to be hugely conductive either.
Gotcha.
Because it's an equipotential surface anyway. It's metallic.
Yeah, right.
So it's not this mat is not designed for carrying huge fault currents. It's designed to protect against step voltage from lightning strikes, perhaps touch voltage, although very hard to mitigate with lightning if you're close to the source, as well as up to 22 kilovolts of electrical fault isolation as well.
Okay.
So yeah, it's quite a unique sort of beast, this one.
Really interesting. Yeah, I'm trying to picture it in my head as you speak. Now so we've got this lightning protection. And traditionally the lightning rods. Can we talk about that, because they seem. I did a little bit of research, obviously, before you came on, and I know a little bit about electrical stuff. And it seems that they come in a weird variety of shapes and forms, and I know there's some secret maths behind all of this. There must be. It's all geometry, let's face it, and ratios. So can you explain some of the traditional shapes they started off with, and their shortcomings, etc.?
Yeah. Well, I mean, let's go back to Benjamin Franklin. So the inventor of the Franklin rod, or the lightning rod. So 1752, I think the date was. So he had, a sharp rod, and the debate of sharp versus blunt started with Benjamin Franklin.
Right.
But it was just a cylindrical, what I call a lump of metal with a sharpened point at the tip. And so he did the very first experiment in lightning protection. But it really wasn't until the 1900s, probably around 1930, that we actually started to understand what lightning is, around the 1930s. But during that time, sharp, and Franklin had basically concluded that sharp rods were the best way to dissipate a lightning strike, to attract or capture and dissipate a lightning strike.
Can't use the attract word.
Yeah. Well, it might have been used back then.
Yeah, gotcha.
But then and this is how recent lightning protection research is, but then in the 1980s and 90s came a famous experiment in the United States carried out of New Mexico Tech. So they have very high mountains in New Mexico, the Magdalena Mountains, and New Mexico Tech it's called Langmuir Laboratory. It's a lightning research lab up, and it's 3,500 metres above sea level.
Okay.
So Professor Charlie Moore started this research. He was a professor at New Mexico Tech in the 1970s and 80s. He started this research around the late 70s, early 80s on investigating sharp and blunt again, after it was first talked about in 1752. So we're talking, 230 to 40 years later. So all natural lightning experiments take quite a long time to accumulate data, and they're very complex as well, because if you're going to measure lightning, you have to actually also protect your equipment from the effects of lightning. So they had what were called kivas, underground bunkers, where all the equipment was stored, safe from the effects of lightning, and it was fully instrumented. So they carried out this experiment for many years, and as part of one of my very first overseas trip, I was lucky enough to actually go and be involved with that experiment on the top of South Baldy Peak, it was called, in the Magdalena Mountains, with Charlie Moore. So I met him. He passed away a few years ago, but he's famous in this area. So they concluded quite comprehensively that blunt lightning rods are better at intercepting lightning than sharp rods. So by the time that research had reached a very solid conclusion, I think there'd been 19 strikes to blunt rods and 0 to sharp rods.
So when you say blunt, are we talking about like a slight hemisphere, kind of like an upside down an umbrella effect, or what are we talking about?
This is where it gets complicated.
Yeah,
and
good.
So I wrote a journal paper about this in a few years after that work that Charlie Moore was doing, and I'll explain that in a little bit further. But they were actually basically, just think of a cylindrical piece of aluminium.
Yes.
Rounded at the top, hemispherical at the top.
Yeah, right.
So the radius of curvature was, between 5 millimetres and maybe 20 millimetres.
Okay.
So that, if you think of a hemispherical top. But they were only installed at, if I remember right, it was either 5.4 or 6.4 metres above the ground.
Okay, quite low.
Quite low. Interesting that you say that, because practical lightning protection, you're putting lightning rods on top of buildings.
You're making the lightning rod the highest point.
Exactly. And because it's the highest point, it's much higher, so it's going to look a lot sharper from a lightning protection viewpoint than if it's sitting on the ground.
Yeah.
So what I did was a study using computer modelling. It wasn't an experiment, very impossible to do experimentally. Computer modelling study based on the New Mexico Tech results, but I extrapolated their results to practical scenarios of lightning rods on buildings. And the conclusion was that the radius of curvature had to get bigger and bigger the higher the building and the higher the installation was.
Okay.
And it became 30, 40 centimetres in radius of curvature for the tallest applications. So that sort of work was the beginning of when LPI started in 2002 and developed what are called corona minimising air terminals. That the New Mexico Tech work was the basis of all of that new product development, which started 25 years ago. And it's something we've carried through to the present day. We've improved the design and the materials and so on, and we've had extensive testing done as well.
So they were doing testing with real lightning, or were they creating high voltage stuff from a Van de Graaff generator?
No, it was real lightning.
It was real lightning.
So in the summer, these Magdalena Mountains only get lightning for like 3 months over the summer months, which is, June, July, August in the United States. So it was like a natural lightning laboratory for those 3 months.
Wow.
And then, after that, they'd pack it up and, go and write their research up and then come back the next year. So this has been going on. I think it's still ongoing. It's been going on for over 30 years. But now other researchers have done other studies as well, mainly theoretical or modelling studies, that also agree with all of those early findings, and that is the higher the height of installation, the bigger the radius of curvature has to be in order to be a reliable lightning capture device.
And what does that translate into from a cost perspective? Like, are we talking? I mean, it sounds to me like there's more materials involved. If you're talking about a copper coated rod, and that's what most of the time they're using. No,
we use aluminium's a very common metal in lightning protection.
Right,
and it's much cheaper than copper.
Well, it's more conductive per weight than copper, isn't it?
It's not quite actually, but it's pretty close. So copper is still the best, but the conductivity is not a big deal because the current of the lightning strike multiplied by the resistance of the metal,
yes,
that's a very small number.
Okay.
Where the number gets very big is the inductive part of the whole, chain of components in the process. That's where the big voltage rise occurs. But I mean, just to go back one step as well, I haven't explained the reason why. So I thought you might ask me, but why are the blunt rods getting struck and not the sharp rods?
Can I ask you that now?
Yes, because
so there's a question that puzzles me.
That's a very interesting question that people would like to know. I believe
100%.
And it's very complicated, but I will explain it as simply as possible. The sharper the point, the more corona discharge you get around that point.
Right.
When there's a thunderstorm overhead.
Yep.
So corona discharge is it's the precursor of those upward leaders I was talking about. So every object potentially can produce corona discharge, but the sharper that point, the more of this charge it produces. So if I put a hypodermic needle up, it's going to produce a lot of corona. If I put a sharp Franklin rod, quite a lot. If I put a blunt rod, less. And if I put a ball, a 30 centimetre ball on a pipe, then that's going to produce very little corona. So why is corona important? What happens is when that corona moves upwards, it forms a cloud over the tip of the air terminal of the lightning rod. Mm-hmm. And that cloud of charge actually stops or slows down the reaction of the lightning rod to initiate this upward leader to go and capture the downward leader. So what happens is sometimes lightning will hit nearby but won't be captured by the lightning rod because there was too much corona space charge above the tip. So that is the main conclusion from the New Mexico studies and many other studies since then.
That's really interesting because when you were talking, I was thinking of like pine trees.
Mm-hmm.
They have these needles, these sharp points all over, and they tend to get hit pretty hard in lightning, don't they?
Mm-hmm. So there's a company in the United States, and I won't name the name, but who put their whole model on top of that hypothesis. If I have lots of pointy, sharp points and make lots of corona space charge, lightning won't hit my facility.
You're talking about a dissipated array system.
Yes, yeah. I didn't want to mention names, but it's a general term.
It's a general term. That's what I thought. Yeah.
So look, they don't work. 99.999% of scientists and engineers around the world say you cannot prevent lightning striking a building site or facility, and all the evidence points to that. So you're far better off having a prominent capture point, or points, and capturing lightning and bringing it down in a safe manner and dissipating it into the ground because you can't prevent lightning.
Can I hypothesize? No, I won't hypothesize anything. I'll just suggest it. So you're talking about like the rod that has a convex top, right? What would happen if the top of the rod was concave with the same angle? Would that make any difference at all?
Well, you'll have two sharp points on the edges.
That's the problem, isn't it?
So
you'd have that. Yeah, you'd have that. Yeah, right.
So what we've done with our corona minimising air terminals, just to quickly sidetrack on that, is we've got four stainless steel panels around the outside of the tip. So ours, they're elliptically shaped, and the tip protrudes by about half an inch to an inch.
Are they like an old style child's top?
A little bit like that, yeah.
Okay.
And so that whole air terminal, we have three sizes. We have a small one. It's the size of a mango,
Oh, okay.
approximately.
Yeah, we've got you.
Then we have a medium-sized one, which is the size of a, I don't know, kid's soccer ball, I guess, an undersized ball. And then one that's probably the size of a big, rugby ball or something like that, maybe a bit bigger than that. So we have three sizes for a very good reason. The height of installation requires that you go bigger and bigger the taller you go.
That makes sense from what
Yeah.
we said. Have you ever looked at some of the old buildings? There's obviously ones around Hobart and Melbourne built in 1860s, 70s and 80s. And they have some very unusual, which I assume they're lightning protection on some of their buildings. They have the ball shape, they have the almost like some kind of religious cross shape and all sorts of weird and wonderful. So obviously they had done a little bit of study back then in regards to lightning protection. Is that a fair assessment?
Look, there's a lot of weird shapes, weird and wacko items out there. Our approach is very simple.
But these are old. I'm talking about over 100, hundreds of years old.
Sure.
So,
look, I think they're more for cosmetic purposes than anything to do with lightning protection. But we like to know what the science is behind it, and then actually have done testing in the lab. So there's high voltage labs you can test these devices in to see what their corona performance is or whatever. So we like to put our solutions through all sorts of testing according to standards and things like UL, Underwriters Laboratory as well.
And so these air terminals, is there anything inside them, or is that the secret sauce?
Oh no, some people have things inside.
Right.
And I don't want to speak for other manufacturers or competitors out there, but in terms of corona minimising, without being too brash about it, we're sort of the world leaders in that area because we started it a quarter of a century ago and followed on the back of that research. But in our case, we don't have any active components inside.
Right.
For two reasons. One is you've got to protect those active
components. I was going to say that.
So, lightning's a big, powerful phenomenon. So then it's not working anymore if it gets damaged.
Wow.
Our air terminals, those 4 panels are independent panels, and they respond to lightning coming down via what's called capacitive coupling.
When you say independent panels, what do you exactly mean? Aren't they all connected to each other?
No, they're not connected. So there's black plastic strips in between each panel.
So they insulate.
They're insulated. Now, look, we could have just one sphere, but A, that's hard to manufacture in a practical way. But B, if something happens, right, you've still got redundancy in the system.
That makes sense.
So it's like with earthing, you have 2 bonds off your earth grid. If one fails, at least you've got the second one backing it up.
Wow.
So those panels react capacitively to the downward leader. So it's called capacitive coupling. So the downward lightning has a big electric field around it, and that electric field, it's almost like an electric field sensor. So those panels rise in voltage, respond to lightning. As it gets closer, then things start to happen.
And they're made of the same material as the pointed section?
The tip is stainless steel as well.
Okay.
Because it's lightning can deliver up to 200,000 amps in one strike. Okay, and look, in years ago, aluminium used to be used, but in high lightning areas where it's getting hit a lot, the tip was wearing down. That's how powerful lightning can be. So stainless steel is extremely robust. You'll get some pitting on the surface, but basically it's unaffected.
And there's no thing like I used to own boats and the sacrificial anode on the boat. There's nothing like that involved?
No,
that doesn't...
It's not like a zinc anode.
Right, you know what I'm talking about. Yeah. So you've chosen this stainless steel. Again, I assume it's marine grade.
316. Yeah.
Lasts forever. It's the toughest stuff out there. Robust, minimum pitting. So it's going to last a very long time.
They're maintenance free, and they last 25 to 50 years. They've been out there for a long time, and unless you get an absolutely rogue, ferocious lightning strike,
you can't get. Yes,
it can even damage the air terminal. But it's a very rare phenomenon actually to see damage to the air terminal. So it's the surge protectors that wear out.
Right.
So any manufacturer of surge protection will tell you that surge protectors wear out, and they do.
Okay.
And that's the metal oxide varistas inside those components that actually deteriorate because they're taking all the hits.
They're taking a pounding, basically.
They're taking a pounding, and eventually they wear out, and then you just replace them when they wear out. So those require a little bit of maintenance, and that's to monitor the status. But air terminals are very maintenance free.
So let's say I'm a commercial solar ground mount and roof mount. Let's say in parts of Australia that definitely require lightning protection. What's the process? What's the process for me to go? Well, I definitely need lightning protection, but I'm not sure how we should go about this. Do I come if I came to you and said, Franco, we're about to do a 5 megawatt system. It's in just near the Atherton Tablelands. There's a lot of energy, lightning issues, weather. What do I need to do? What are you going to? How do we go from here?
So I'd ask you, have you done a risk assessment first?
And my question is, Franco, what's a risk assessment?
So the Australian standard has a lightning risk assessment. Now, it's really geared towards ordinary buildings.
Yep.
So it's a bit of a stretch to do solar farms and commercial solar and, wind turbines and wastewater treatment plants and things like that. But you can do it, or you've got to do specialised calculations. But for a 5 megawatt solar, it's probably not too difficult.
Right.
So you can look at what the risk level is, and that gives you some guidance as to whether you need direct strike and or surge protection. But remember always, if you're going to protect, there's the 4 steps to look at. Direct strike, surge, earthing and bonding, and protecting people. Now, with commercial solar, I'd say that's not relevant. The protecting people, because you don't have people working outside during the operational phase.
True.
Of the solar. So it'd be those 3 steps. So take care of those in a cost-effective manner.
And would you do a geotech survey of the ground? I mean, is that something that, or whether you do it or not, is that something that's part of the process to see what kind of soil what's that conductivity of the soil?
Yeah, well, geotech is for civil and structural engineers. Not very useful for electrical stuff. So you do soil resistivity measurements.
Yep.
And that gives you an idea of the conductivity of the soil and how much earthing you would need to put in to get below 10 ohms, for example, if you wanted to use a 10 ohmic target for that installation. The other way to go about it is you can do it by trial and error, which is not...
Don't like the sound of that.
It's the way earthing's been done for decades, but is not done these days.
But there's enough data out there. I mean, we don't have to go trial and error. That sounds... Yeah. Because it may be a case, Franco, for instance, the 5 megawatt solar farm, our client has stipulated we must have lightning protection.
Yeah.
So
then you just do a quick soil resistivity survey. It doesn't take long, and then you can design your earthing system per whatever criteria you're trying to meet. So for lightning protection, it's 10 ohms or less, but obviously for electrical protection, you've got to make sure step and touch voltages are also not exceeded. So that'll depend on what standard you're using and so on.
And what standard? I mean, there's IEC, there's the Australian standard, there's the French standard, and Sam asked me to ask you about the French standard, and I know you know Sam well. What what is the best approach? I mean, does one supersede the other? What's going on with this?
So, look, the important thing about standards is, in lightning protection I'm talking about, none of those standards are mandatory standards.
Why? That doesn't make sense to me.
Well, lightning's always, I hate to say, it's always been an afterthought in projects traditionally. But it shouldn't be, because especially in today's day and age, you've got so much modern sensitive equipment, and downtime also is very expensive as well. So
because we offer, let's say this scenario, we've offered our client a minimum production guarantee, and if we have downtime, it costs us.
Exactly. Yeah. So the way to prevent that from lightning is lightning protection.
Yes.
But I mean, a mandatory standard is AS 3000.
Yep.
So the wiring code. So electricians have to follow that step by step, because it's mandated in law. Lightning protection standards are not mandated in law. So that my point about that is that you can select different standards for different projects based on what is the best solution for that project. Right. So a couple of the projects we've already done with Greenwood have taken that approach, and that's the approach we've used for the last quarter of a century, is horses for courses. What's the best approach?
We did a floating solar. So for those you don't know, 350 kilowatt floating solar. So you're talking about high density polyethylene floats, solar panels, and all the cabling going back to the land, and obviously inverters and transformer, et cetera, What was different about that from a earthing perspective, apart from the fact that they're floating? Which leads me to the other question: can you earth into the water?
Absolutely. Actually, the water is the best earth you can have.
Right. But in this situation, we didn't earth in the water, did we?
To be honest, I'd have to dust off the thing. But you've got land-based equipment as well. So obviously you need to look at the earthing, overall earthing scheme.
Of course.
Yeah.
Okay, so we're talking because in this situation, all the circuit protection, etc., is the AC breakers.
It's on land.
It's on land. So the lightning protection is following the same route from a cabling perspective back to the inverters, back to the interface protection, main switchboard, etc., etc.
Just to give you an example about water, we do a lot of vessel lightning protection. So these are defence vessels, police, coast guards, commercial vessels, recreational vessels. Right. You wouldn't believe the number of inquiries we get in that area is increasing all the time.
Well, it makes sense. You
yachts
told me.
As well.
As you said, if you're on a flat body of water and you're a boat, you're the one sticking out the...
So St Elmo's fire, for those listeners that don't know, is a red glow on the tip of the mast, and it's the precursor to it being struck by lightning. So St Elmo's fire is a well-known thing to sailors.
Yes.
So anyway, when we do vessel protection, earthing's the least of our worries. So if the vessel's metallic, it's already earthed. Yep. It's sitting in the water, whether it's fresh or seawater. Seawater's much better than fresh water, but fresh water's better than soil on land.
Yes.
So you've already got your earthing. If it's a non-conductive hull,
like fiberglass,
you put a metal plate under the hull, just a small metal plate that's always in contact with the water. That's all the earthing you need.
Wow.
Because lightning current's going to go into that plate and then just spread out throughout the water and say, thank you very much, this is a low
because there's a lot of new plastic hulls coming on the market as well, and they'd be the same scenario.
That's all you do.
They? But with an aluminium hull, you've already got the aluminium. There's your plate, the whole hull.
Yep.
So it's really simple as that.
It's as simple as that. But what's not simple is the protecting all the communications equipment and
that's what I was going to say.
Yeah, which is what we do with our air terminals, our advanced air terminals, and we use an insulated cable as well to isolate the vessel from the lightning currents, so that we bring the lightning straight down to that metal plate or the hull and dissipating it into the water without electrifying anything else. So that's called protection by isolation.
What about a situation where you've got, and I don't know if I'm wrong here, like a recreational vehicle, right? That's got a standalone system on it, etc. How do you earth a vehicle? And should you earth a vehicle?
To be honest, we don't do a lot of lightning protection of recreational vehicles. But look, for example,
is it a silly question? In other words,
no, it's not a silly question. Actually, there's an antenna company in Hobart that used to be right next door to us when I first started in lightning protection, and they developed antennas for mobile vehicles on land.
Okay.
And you don't have a solid earth in that case. But I mean, if you were doing lightning protection, you probably have to have just a trailing chain coming off the chassis of the vehicle,
like the old style anti-car sick.
Something, a little bit like that.
Okay.
Because if you only rely on the tyres, it could blow up the tyres as it discharges itself. It's going to go to ground regardless. So the thing to remember is lightnings come from 5 kilometres away. So the thundercloud's typically 5 kilometres high, give or take a few kilometres. So it's broken down 5 kilometres of air, and air is a fairly good insulator.
So we're talking huge energy.
Yeah, so once it lands on a vehicle, right, the tyres that are only, let's say, 15 centimetres thick in terms of distance to cover, it's just going to flash straight over that.
Okay.
And if it does that, it could blow the tyres up as well. So
wow. Now I know,
or it might just go to ground quite safely, and nothing happens. You don't even notice it.
Okay, yeah. Thanks for clarifying that. Now, sporting fields seem to be one for me that logically require lightning protection, because we're talking about these large galvanised, hot-dip galvanised towers with. Well, they used to be metal halide, low pressure, high pressure sodium. Now they're moving to LEDs. But we're talking about 20-metre structures. Some of them are like a seesaw style. Is that a big part of the business? Those kind of lightning protection on those?
Not huge, but they're quite simple to protect.
Right.
You put an air terminal on top of the light towers.
Right.
And whether you use the tower as the down conductor or whether you would do it in an insulated manner would depend on this, if you got sensitive electronics or whatever in the system. But more often than not, you just use the tower as the down conductor to bring the lightning to ground.
Okay.
So then you just have to make sure they're earthed properly, remembering our third step.
Yes.
In the plan is the earthing. Sporting grounds are pretty straightforward, but you have to think about what are you protecting in that case, right? Because even if you successfully capture lightning to one of those towers, so for example, the Gabba in Brisbane has lightning protection on those towers, but you're capturing the direct lightning strike, but lightning's getting injected into the ground. If there's people standing on the ground, step voltage is a hazard mechanism from a lightning strike.
Oh, that makes a lot of sense.
So that's why you need lightning warning as well. People shouldn't be outdoors when lightning's striking in the immediate area within 8 to 10 kilometres. So lightning can actually step. So it can strike in one place and strike 10 kilometres away at the same time. So
wow, 10 kilometres?
10 kilometres.
Wow.
So this is called multiple ground terminations. It's a phenomenon that was discovered about 20 years ago. So we're still learning a lot about lightning, but that's where the 10 kilometres, so 10 kilometres is sort of the minimum range over which you should get indoors.
Right.
So 10 to 15 kilometres. So 15 is a bit more conservative, but 10 I would say is the sort of minimum thing for warning people.
So that's part of the whole strategy, is having that warning system. That's really interesting. My daughter plays soccer, and there was a game that they said, look, it's raining, there's lightning somewhere, let's stop it, and they did. And I think also they didn't want the kids to get too wet, kind of thing. Does your business also deal with architects at the build stage of, say, a high-rise building, for instance? Because that's, to me, that would be the logical point where you go, hang on a sec, you're doing your earthing anyway, you're bonding. You should be getting involved in that stage, shouldn't you?
Yeah. No, and we do. We deal with architects and consultants and contractors all the time. And our advanced air terminals, architects love those, actually, because they're quite aesthetically pleasing.
And that plays
Instead
a
of
role.
having 50 spikes around the building and lots of down conductors draped down the sides,
Yes.
we can replace that with an aesthetically pleasing, centrally placed, tall air terminal, and then run the insulated cable down like a vent shaft in the building, so it's completely disguised.
Yeah, that makes sense.
Yeah, so no, the architects are quite on board.
Well, aesthetics does play a role. I mean, and I've seen pictures of the air terminal, and they look good. They have a nice shape to them, right? And I'm sure the secret's in all the maths and the ratios, of course, and the thickness of the material and you know how they're all placed. Now, with solar farms, we have an issue, well, potentially an issue of anything that if a lightning rod or anything is put on top of that top edge of the panel, it has the potential to shade the row behind. How do you sort of mitigate that?
We have never done a solar farm that way.
Right,
That's
right.
with conventional protection because you need so many of those Franklin rods.
That's what I thought. Yeah.
I think we did. There was I can't remember how many megawatts the solar farm was. This was overseas, but we needed 1,100 Franklin rods versus 35.
Oh, crikey.
So what we do, we've done over 50 gigawatts of utility scale solar overseas, mainly India, but some other countries as well. And we use Stormmaster ESC 60 air terminals. So it's an early streamer emission technology according to the French standard.
Right.
And on an 8-metre mast, so these get installed on a galvanised pole, those cheap as chips for that. On top of that, one of those will protect about 1 megawatt of solar panels. So,
oh, wow. So you could put that right at the back of the array, not shading anything.
Yeah, you can put it in places where the shading's not a factor.
Yeah,
and this is what happens all the time.
Right.
So, I mean, for example, for like a 300 megawatt solar farm.
That's a big one.
Yeah, it's pretty big.
Yes.
You need, 250 to 300. It depends on how the circles overlap.
Right.
So the protection areas, you've got to get them all overlapping so there's no gaps in that scheme.
Now, you mentioned protection circles. Are we talking the rolling sphere approach? And forgive me, that's about all I know. I know there's about 3 different kinds.
There's many different methods for positioning lightning rods. So rolling sphere is one of the sort of traditional ones.
Yep.
It comes from the 1950s and 60s type era. It's in a lot of standards, but that one is positioning conventional Franklin rods.
Oh, okay. That deals with the standard spiky rod.
And you need lots and lots of those. But there's other methods like the ESC standard, for example, calculates the protection area based on some other principles. It's called a time advantage for those upward leaders.
Yep.
You measure the time advantage in the laboratory, so it all has to be properly done with a proper test. And the protection area is about 100 metres approximately, but on a 8 to 10 metre high pole.
Gotcha.
So that's where the 1 megawatt of solar panels comes from. So for a 5 megawatt system, you could probably get away with between 3 and 5 of those.
That doesn't sound like it too
very
expensive.
cost effective.
I was going to say, it sounds very cost effective. As opposed to the spiky rod, the Franklin rod approach would be like, as you said, hundreds of them.
You'd need a lot, and then you've got the shading issues as well.
This is the thing. And it's very obviously, obviously where the arrays go, they have great sunlight, etc. But you do not want to be shading one array or one what they call table from another. It's obviously really important. Are you active in trying to get this lightning protection as a mandatory thing, like, you know, from a standard perspective? I mean, is that something that you've talked about or involved in?
Not really. I mean, to be honest, I don't know how one would go about that.
Okay.
Whether it's the standards organisation or whether there's some other driver for it.
Right.
Like insurance companies.
Okay.
So, you know, insurance keeps getting mentioned sometimes when I'm giving presentations, and I'm still yet to see what the wording is like around insurance companies wanting lightning protection. But I'd say that's probably more of a driver than on the standards front.
I think it's like thermal imaging of a switchboard on a regular basis from a maintenance perspective. It should reduce the insurance premiums, etc., but how much we don't know. It's case by case.
Yeah.
And
if you look at lightning too from a risk viewpoint, so the acceptable risk, acceptable's not the right word to use these days, tolerable risk for lightning, for human deaths, serious injury or death due to lightning, the tolerable risk is 10 to the minus 5. So for our listeners who might not know mathematically what that is, that's 1 in 100,000 probability.
Yeah, right.
So, for example, if 100,000 people were gathered somewhere and you did lightning protection, you'd be accepting a risk that one person would die on that particular day or in that
thought.
year.
Yeah.
It's a horrible way to look at it,
but
that's how the risk thing is looked at. So I guess, you know, if something's mandatory, then the risk level would have to be so much tighter than that. And I don't know what the risk is for AS3000, for example.
I don't know either, actually.
But that's probably the main driver for something being mandatory versus not voluntary, but a guide or a recommendation. So,
for anyone listening out there who is like in the process of putting together a wind farm, a solar farm, what's the best advice? How do they get in contact with, you know, LPI?
Well, we're easy to contact.
Yeah.
But the best advice is remember the systematic plan for lightning protection. So if that's implemented properly, doesn't matter what the industry is or what the site's like, if that's implemented systematically, you're on the way to reducing the risk by 90+% to that facility. So then it's a matter of what's the best solution to implement and what's the most cost-effective solution.
Yes.
Because whether we like it or not, cost always comes into it. So
tell us about it. It really, like, everything's tempered by the economic reality of the world we live in, and that's just how it is. Look, I think we've just touched the tip of the iceberg. Maybe down the track, Franco, you come in for a part 2. We can go nitty gritty as I learn a little bit more about this. Thanks so much for coming in. We've had a lot of correspondence over the last few months, and I'm really glad it's finally resulted in this particular podcast discussion, and hopefully you've enjoyed yourself. And
look, thanks for having me, and it's been a much more pleasurable experience than what I had imagined.
I could tell.
So
good. I saw the look on your face when you walked in.
A little bit of a relief. So yeah, I mean, I'd definitely be up for a follow-up session where we can go into more detail on some of these topics.
That's great. Thanks very much, Franco. Cheers.
Thank you very much. Bye.